Hi everyone, we are back, and now let's get into how do we want to calculate plane stress states easily with eigenvalues and eigenvectors. So one of the most important things is figuring out how can we find the stress state or the rotation that gives us only normal stresses. So we figured out last time, and actually we can kind of test this out to make sure that we get eigenvalues is going to give me the actual values. And last time we knew that the rotation in that basically around the 3-axis of this 19.3 degrees. So actually we can kind of pull this out here. Oops. This was that 19.32 value we had previously. So if I apply this rotation matrix around my 3-axis, or basically to the my basically my original coordinate system, my 1 direction, 2 direction, 3 direction, I could get my new test or my new basis set. I could also, this would be my basically new vectors, old vectors, and actually we could go ahead and let's go ahead and build our Q matrix right here. So we could use basically the same kind of setup here for this Q, and then we could also do basically stress1.q. So let's go over here. So for example, I could take, we should be able to recover this. So I could do Q, I could say this is new test, basis here, I could do this, and then you can see 16.43, everything else is 0. So, but again, we figured that out last time. But how can we actually deduce that by using kind of these eigenvector values and not having to do so much work? So I could get the values here, I could also get the eigenvectors directly, and again, I could build that Q matrix here, and again, you can see same values. Very, 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 very good. And you could then back out and figure out the angle as well. And you see that this matches with our Voigt notation as well. So this is very good, and you could, again, do the same thing with the rotation matrix as well, get a cleaner value. Again, everything is the same. We're seeing the same answer and over and over and over again. But I could do this with a random tensor as well. So let's say I have this complex stress state here. I could prove this is a stress tensor because the transpose is equal to my stress random. I could find my eigenvalues. I could find my eigenvectors here. I could then, again, look at the basis here, look at the eigenvectors of the stress rand. I could get my new Q. Look at 202 minus 155.08, 39. Excellent. I could rotate this any random direction I want and get those values out. I can double check this answer with my new Q here. You see I get the same results here, by just some arbitrary rotation. Again, either by just doing the rotation matrix directly, or by applying it to my system and using the Q as well. And that's pretty much it. Now, you'll notice here, if I just do like that T over here, you see the answer is not symmetric. That's the key thing. Once I have a full 3D stress state here that is not plane stress, I can't apply that, this one was a, rotation matrix of 3 by 3, but this only applied for that plane stress state, and I needed to dot it with that 1 by 3. So make sure you use either the rotation matrices or you use your Q, and then we can rotate freely. And then you can solve lots of cool mechanics problems. So that's it. So hopefully we've kind of applied these linear algebra concepts where we get into a system that's very useful, and then now it's on to Fourier analysis. So I'll see you in the next video. Thanks.